In this presentation, we provide a detailed, rigorous, and clear derivation of Feynman's path integral equation of quantum mechanics. We have tried to develop the theory in as much generality as possible, without compromising the clarity and simplicity of a more elementary treatment of the subject. We start with the well-known Schrödinger's equation, which presents a differential, or local view, of how the state of a quantum mechanical system evolves over time. On the other hand, Feynman's path integral equation provides an integral, or end-to-end description, of the same state evolution process. In doing so, it connects quantum mechanics to the well-known classical principle of stationary action of the system Lagrangian. Schrödinger's differential equation says that the quantum mechanical state of a closed system evolves in accordance with where psi of t is the state of the system at time t, and h op of t is the Hamiltonian operator of the system. The equation also features the imaginary unit, I, and the normalized Planck's constant, h cross, which is equal to the Planck's constant, divided by 2 pi. This equation shows that the time derivative of quantum mechanical state is governed by its Hamiltonian operator. The above differential equation has an explicit solution of the form where u op of t, t0, is called the time evolution operator of the quantum mechanical system. Note that u op is a function of two variables, the current time t, and the initial time t0. The time evolution operator u op satisfies a simple initial condition, as well as a first-order, partial differential equation. It may be verified that, if the Hamiltonian operator is Hermitian symmetric or self-adjoint, then the corresponding time evolution operator is an isometric, or a norm-preserving linear operator, on the underlying Hilbert space. In finite-dimensional vector spaces, this is equivalent to saying that u op is a unitary operator, whose two-sided inverse coincides with its adjoint. Copying over, we have isometry, or norm-preserving property of the time evolution operator is noteworthy, because it implies that Schrödinger's differential equation preserves the norm of the quantum mechanical state. In other words, as a result, if the initial state of the system has unit norm, then the quantum mechanical state of the system continues to have unit norm at all other times t. Consequently, there is no need to explicitly renormalize the state vector after applying Schrödinger's equation. We now come to the main topic of this presentation. Let us revisit our formal solution to Schrödinger's equation. This time, we have written the equation using Dirac's, ket, and bra notation. Left multiplying both sides of the above equation with the adjoint of a position basis vector, we obtain. We note that the inner product of the quantum mechanical state vector with a position basis vector yields the position wave function. Hence, the left-hand side of our equation may be identified with the position wave function of the system at time t. Next, on the right-hand side of the equation, we insert the identity operator between the time evolution operator and the state vector at time t0. In summary, we have our next move is to expand the identity operator in the position basis. In other words, using the generalized orthonormality and completeness property of the position basis vectors, we may rewrite the identity operator in the above equation as follows. Rearranging the terms, we obtain. Once again, we recognize the position wave function of the system, evaluated at time t0, appearing on the right-hand side of the equation. So, we now have the position wave functions of the system on both sides of the equation, evaluated at different times. The two wave functions are connected via a complex-valued integral kernel, defined by we refer to this as the time propagation kernel of the given quantum mechanical system. With this notation, our equation becomes. This is an equation that transforms any given wave function of the system at time t0 into the corresponding wave function at another time t, as dictated by Schrödinger's equation. Consider the special case where the initial wave function of the system has the form for some fixed, n-dimensional vector, x0. Roughly speaking, this corresponds to a classical state, wherein the system has a well-defined position. In this case, our equation implies this shows that the time propagation kernel K is indeed the impulse response of the above state transformation from any given time t0 to any other time t. In particular, the time propagation kernel defines how a momentarily localized wave function spreads over position space as time goes by. This brings us to our main problem statement. Our main interest is in evaluating the time propagation kernel K explicitly in terms of the classical Hamiltonian function of the system. It turns out that the time propagation kernel is more directly related to the classical Lagrangian of the system, which of course is a close relative of the classical Hamiltonian. Derivation of the path integral representation of the time propagation kernel is going to take some time, but we don't want to lose our bearing during the process. Hence, we first provide a broad outline of our approach, and then flesh out the details. Here are the main steps in our derivation of the path integral equation. Our very first step is to express the propagation kernel K in terms of the so-called one-shot propagation kernels that are simpler to evaluate. Note that the time propagation kernel is natively defined in terms of the time evolution operator UOP of TB, TA, but we would much rather work with its underlying Hamiltonian operator HOP of T. To this end, our first step is to eliminate the time evolution operator from the picture in favor of the Hamiltonian operator. This is the motivation for step 1. In our second step, we establish the precise relationship between the quantum mechanical Hamiltonian operator and the classical Hamiltonian function of the system. It turns out the result holds for any real or complex valued function f of a real or complex valued input argument. Here, bra of p and ket of x denote the standard momentum and position basis vectors respectively, which are well known to be Fourier duals of each other. Our third step consists of two subparts. In step 3a, we evaluate the one-shot propagation kernel, K1, wherein L denotes the Lagrangian function of the system, and L sub c is the so-called critical length of the Lagrangian function. The ratio U sub k represents a sub-path velocity of the system. In step 3b, we evaluate the critical length L sub c of the system Lagrangian, which is a function of 4 parameters. A position vector x, a sub-path velocity vector u, a time instant t, and finally, a time interval delta tau. That brings us to the fourth and final step of our plan, which also has two subparts. In step 4a, we synthesize the original time propagation kernel K by combining multiple one-shot propagation kernels tilde K sub 1. Next, we pass to the limit as the time interval tau k minus 1 shrinks to 0, leading to the famous path integral equation. We now discuss each of the above steps in detail. The first step is about expressing the time propagation kernel K that involves the time evolution operator UOP in terms of one-shot propagation kernels tilde K sub 1, which involve the Hamiltonian operator HOP. Recall that our ultimate goal is to relate the time propagation kernel to the classical Lagrangian, or the classical Hamiltonian of the system. But first, we need to relate it more explicitly to the quantum mechanical Hamiltonian operator of the system. We are essentially looking to eliminate the time evolution operator from the picture in favor of the Hamiltonian operator. Recall the defining equations of the time evolution operator. It reduces to the identity operator and the two time variables are the same, and it follows a first-order, linear partial differential equation with respect to the first time variable. This provides an implicit relationship between the time evolution operator and the Hamiltonian operator, but we are looking for an explicit, functional relationship of the form a function g of the Hamiltonian operator HOP, possibly at various time instants tau. Under some important, special cases, we can solve the above differential equation explicitly, and obtain an exponential relationship between the two operators. In particular, If the Hamiltonian operator is time invariant, then solving the Schrödinger's equation in closed form, we see that in this particular special case, time evolution operator UOP is obtained by exponentiating the Hamiltonian operator HOP, suitably scaled with the time interval, and some other constants in the exponent. As we just saw, on the other hand, if the Hamiltonian operator HOP of t varies with time, but commutes with itself at different times, we can still solve Schrödinger's equation explicitly, but this time, we obtain a time integral of the Hamiltonian operator in the exponent. In the most general case where the Hamiltonian operator at different times may not commute with one another, the relationship between the Hamiltonian and the time evolution operator gets more complicated. Nevertheless, the following relationship holds in general. This means, the relationship from the two special cases earlier still holds over small time intervals, but only approximately. Furthermore, the approximation error goes to zero, with the square of the time interval from t sub 1 to t sub 2. To establish this result, consider the Taylor series expansion of any twice differentiable function. For some intermediate value tau, between t sub 1 and t sub 2. Equivalently, we may write the following. From Taylor series analysis, we have considering the special case. For some fixed t sub 1, we obtain which implies from Taylor series expansion of the time evolution operator, we have obtained. On the other hand, Taylor series expansion of the exponential function yields subtracting one equation from the other, we obtain the desired result. Copying over, we have moreover, we have this means that the error coefficient b is bounded above, as long as the norm of the Hamiltonian operator and its time derivative are both continuous functions of time. We now have an explicit relationship between the time evolution operator and the corresponding Hamiltonian operator, albeit an approximate one. But we shall utilize it, and eventually make it exact, by taking the appropriate limits, at the opportune moment. But before we can do that, and evaluate the time propagation kernel K, we need one more important ingredient. That brings us to the semigroup property of the time evolution operator. To establish this, we exploit the fact that Schrödinger's equation has a unique solution for any given initial condition. Therefore, the explicit solution we presented must be the only possible way the quantum mechanical state of a closed system can evolve. Now, let psi of t0, psi of t1 and psi of t2 denote the quantum mechanical states of a system at times t0, t1, and t2, respectively. While one of these states may be picked randomly, the other two states are completely determined by this one choice, in conjunction with Schrödinger's equation. As a result, combining this system of equations, we obtain, since the above equation must hold for all choices of the initial state vector psi of t0, we conclude that thereby establishing the semigroup property of the time evolution operator. Copying over, we have an important special case is obtained by setting t sub 2 equal to t sub 0. In this case, the semigroup property reduces to in finite-dimensional Hilbert spaces. This implies where the last step holds, because the underlying Hamiltonian operator is self-adjoint, thereby ensuring that the time evolution operator is unitary. We now combine the semigroup property, along with our previously established lemma, in order to evaluate the time propagation kernel K, defined earlier. We are now ready to introduce the product decomposition of the time evolution operator. To exploit the semigroup property of the time evolution operator UOP, we first break up the given time interval from t sub a to t sub b into a large number of infinitesimal time intervals, where n is a large, positive integer, delta tau is the duration of each small subinterval of time, while each tau sub k is an endpoint of one or two subintervals. Clearly, tau sub 0 coincides with t sub a, while tau sub n coincides with t sub b. As a result, where in the last product expression, the index k is incremented from right to left. The product decomposition in the last two steps is a consequence of the semigroup property. We start with the product decomposition and use the approximate relationship between the general time evolution operator and the corresponding Hamiltonian to obtain expanding out the n-fold product yields, which includes the main product term, along with a sum of residual or error terms, scaled with binomial coefficients as shown. Focusing on the residual terms, we obtain, to begin with, we have used the explicit bound on the big O terms, that was developed earlier, as a lemma. Next, we upper bound the binomial term n choose k, with n power k. This results in a finite geometric series, which may be simplified, and eventually upper bounded by a linear term in delta tau. So, the overall approximation error is on the order of delta tau, which is equal to the overall time interval divided by n. Clearly, delta tau goes to 0, as n goes to infinity. To summarize, we have the residual or error term is linear in delta tau, and hence inversely proportional to n. We may use this product decomposition to evaluate the time propagation kernel, k. We start with the definition of the time propagation kernel, replace the operator UOP with the approximation we derived from its product representation. This yields a sum of two components, the main term, which we denote by tilde k sub n, called the n-step propagation kernel, and an error term, that is on the order of delta tau. Henceforth, we will focus on the main term on the right-hand side. To get an intuitive feel for our next move, let's consider the special case, where the number n is equal to 3. We write out the threefold product more explicitly. We insert the identity operator between each of the terms in the product. We replace each identity operator with a system of position basis vectors, based on their generalized orthonormality and completeness properties. This results in a product of three one-shot propagation kernels, connected via a double integral, evaluated over all points in position space. Extending this logic to arbitrary positive integers n, however large, we obtain where we recall that tau sub 0 coincides with t sub a, while tau sub n coincides with t sub b, which constitute two of the input parameters to the original time propagation kernel. To summarize, the n-step propagation kernel has been reduced to a product of one-shot propagation kernels, interconnected via a multiple integral of order n-1. The one-shot propagation kernel is formally defined by wherein delta tau is the duration of each subinterval. Recall that in the case of a time-invariant Hamiltonian operator, we have, which means so in this special case, the full time propagation kernel coincides with the one-shot propagation kernel over the entire time interval from t sub a to t sub b. This completes step 1 of our high-level plan. Our next goal is to evaluate these one-shot propagation kernels for general, time-varying, Hamiltonian operators. We already have an explicit relationship between the one-shot propagation kernel and the quantum mechanical Hamiltonian operator. Our goal as you recall, is to tie this in with the classical Hamiltonian function. To this end, we begin step 2 of our action plan, which is to establish the precise relationship between the quantum mechanical Hamiltonian operator and the classical Hamiltonian function of the system. It turns out, which is valid for any real or complex function f. Here, vectors p and x denote the standard momentum and position basis vectors respectively, which are well known to be Fourier duals of each other. To establish the result above, we invoke the theory of spectral decomposition of normal operators. We recalled that in finite dimensions, any family of mutually commuting, normal operators, may be simultaneously diagonalized, by choosing an appropriate orthonormal basis, for the underlying vector space. This result generalizes to infinite-dimensional, bounded, normal linear operators, as well. And this is applicable to the Hamiltonian operators, because they are self-adjoint, and hence normal linear operators. At any given time instant t, the spectral representation of the self-adjoint Hamiltonian operator is given by where the linear operators p sub h, t of lambda constitute the density of an orthogonal projection-valued measure on the set of real numbers. In simple terms, it means that for any measurable subset of real numbers S, the Lebesgue integral is an orthogonal projection operator, in the sense that in addition, we must have the completeness property of the measure, in the sense that integrating the projection density over the entire basis space must yield the identity operator on the Hilbert space. We are able to restrict the domain of integration to real numbers, rather than complex numbers, because the Hamiltonian operator is not only normal, but also self-adjoint, which means that its spectrum is purely real. Armed with its spectral representation, we proceed to explore the matrix elements of the Hamiltonian operator, where we have the standard momentum basis vector on the left, and the standard position basis vector on the right. Using the spectral decomposition of the Hamiltonian operator, we see that it stands to reason that the matrix element of the Hamiltonian projection density is non-zero, only when as a result, for any real or complex measurable function f, the following equation must hold. Which is just another way of saying, either the matrix element is 0, or f of lambda equals f of h. Integrating both sides over all real numbers lambda, we see that taking the integrals on the matrix elements into the matrix itself, we get we simplify the left-hand side, using spectral representation of the Hamiltonian operator. Likewise, we use the completeness property of the projection-valued measure to simplify the right-hand side. Thus, we have a closed-form expression for the Hamiltonian operator matrix elements, in terms of the classical Hamiltonian function of the system. In summary, our calculations have shown that from this, we obtain an explicit representation of the quantum mechanical Hamiltonian operator, in terms of the classical Hamiltonian function of the same system. Indeed, we use the fact that any linear operator is completely characterized by its matrix elements, in the sense that of course, in the first step, we have used the completeness property of the standard position basis, as well as the standard momentum basis, a recurring theme of many of our calculations here. The above result holds for any measurable function f, including of course, the identity function. We have thus discovered an explicit relationship between the classical Hamiltonian function and the quantum mechanical Hamiltonian operator. It is worth reiterating that our previous result holds for any measurable function f. We may relate our findings to the one-shot propagation operator by defining the measurable function f to be a complex exponential function. This yields This is all well and good, but on the left-hand side of our equation above, we have the momentum basis vector on the left, multiplying a function of the Hamiltonian operator, whereas the one-shot time propagation kernel has position basis vectors on both sides of the exponentiated Hamiltonian operator. To rectify this problem, we resort to our usual trick of inserting the identity operator in the middle and expanding it in the standard momentum basis. That brings us to step 3. Recall that our charter for step 3a is to evaluate the one-shot propagation kernel, wherein L of x, v, t is the classical Lagrangian function of the system. U sub k is the average subpath velocity, and L sub c is the critical length of the Lagrangian function. We recall that, for any measurable function f, vector x sub k minus 1, vector x sub k, and time t, as suggested earlier, we insert the identity operator and decompose it in the momentum basis. By reassociating the terms, we extract the position momentum inner product and a matrix element of the Hamiltonian operator. Using the result of step 2, we obtain the classical Hamiltonian function and a pair of position momentum inner products. Since the position momentum inner product is a complex exponential, we obtain now, setting. We obtain the following expression for the one-shot propagation kernel. In the last step, we have simplified the first term in the exponent by introducing the average path velocity vector. The key term in the exponential above is beginning to look somewhat like the classical Lagrangian of the system. Indeed, the classical Lagrangian and Hamiltonian functions are related via the Legendre transformation. Motivated by this, we make a change of variable from vector p to vector v, as shown above, in the integral expression for the one-shot propagation kernel. With such a change of variables, the main term within the exponential becomes So, we start with the integral expression for the one-shot propagation kernel. Perform a change of variable from vector p to vector v and obtain where denotes the Jacobian of transformation, which we assume is non-zero. We rewrite our expression for the one-shot propagation kernel as follows. Where we add and subtract a Lagrangian term in the exponent without changing the value of the right-hand side expression. One of those terms is pulled into the integral, while the other term remains outside. Next, we define the overall exponent within the integral to be the differential Lagrangian. To summarize, we have a new expression for the one-shot propagation kernel, where the differential Lagrangian function is formally defined by Let's denote the integral. We note that the complex-valued parameter L sub c has the dimensions of length or distance. We shall refer to this as the critical length of the Lagrangian function. With this definition, the main result becomes in the special case of a time-invariant Hamiltonian, this is also the time propagation kernel, and so we are done. Indeed, where u is the average path velocity between the endpoints. Recall the explicit relationship between the quantum mechanical Hamiltonian operator and the classical Hamiltonian function. From this, it is obvious that the Hamiltonian operator is time-independent, if and only if the classical Hamiltonian function has no explicit time dependence. This is equivalent to the condition that the Lagrangian function has no explicit time dependence. In this case, the critical length, just defined, is also independent of the specific time instant t sub a. It depends only on the time interval t sub b minus t sub a. Taking all this into account, the time propagation kernel of a time-invariant quantum mechanical system is given by. This is the complete solution for the time propagation kernel for any time-invariant system. In this special case, step 1 and step 4 may both be skipped. We only need steps 2 and 3. But in the general case, we need to plot on and synthesize the time propagation kernel over a finite time interval in terms of the one-shot kernels derived in step 1 and simplified in step 3a. This brings us to step 4. Where S is the classical action along a particular system trajectory defined by the precise meaning of these last two expressions will be clarified as we go through their derivation. We start with our finding in step 1, where we approximate the original time propagation kernel with a n-step propagation kernel for some large positive integer n. Next, we break up the n-step propagation kernel into a product of one-shot propagation kernels, along with n-1 nested integrals. Next, each factor in the integrand is expressed in terms of the exponential of a Lagrangian, along with a normalization factor, represented by the critical length of the Lagrangian. We note that the terms within the exponential are just scalar quantities, not linear operators. Hence, the exponential terms may be multiplied by simply adding up the exponents. The overall exponential term in the integrand is a sum of Lagrangians evaluated at different points on a potential system trajectory, each scaled by a small time interval. This resembles the classical Lagrangian action integral, or at least a discrete approximation of the action integral. Apart from this, we also have a residual error term that is linear in delta tau. To summarize, we have derived an explicit, but approximate expression for the time propagation kernel. Indeed, we recognize the average subpath velocities. At different points of that supposed system trajectory. Recall that the expression for the time propagation kernel comprises the nested integral term that we have been talking about, along with an error term that is linear in delta tau. Now, this residual error term on the right-hand side may be driven down to 0 by letting the time interval delta tau shrink to 0, or equivalently, by letting the positive integer n grow unbounded to infinity. In this limit, where the number of nested integration levels approaches infinity, the right-hand side of the propagation kernel equation converges to the so-called path integral, as the term within the exponential converges to the classical Lagrangian action along a path that starts from x sub a, t sub a, and ends at x sub b, t sub b. Also under this same limiting process, the average subpath velocities u sub k converge to the instantaneous path velocities x at tau. This infinitely nested integral, where the integrand comprises an exponential term, together with a normalization term, constituted by the product of critical lengths, provides the formal definition of the quantum mechanical path integral. Within the exponential component of the integrand, we recognize the Lagrangian action integral, formally defined by for any particular system trajectory over the given time interval. We have thus derived the celebrated Feynman Path Integral Equation of quantum mechanics. Note that in this path integral, the domain of integration is the space of all trajectories with the given starting and ending configurations, x sub a, t sub a, and x sub b, t sub b. Each such path makes a complex exponential contribution, or equivalently, a phase contribution, to the overall time propagation kernel. As it turns out, the dominant contribution comes from paths whose Lagrangian action is stationary. Indeed, for any path with a non-stationary Lagrangian action, neighboring paths make mutually negating contributions to the overall integral, thereby rendering essentially all non-stationary paths irrelevant to the net outcome of the above integral. We now have a linkage between quantum mechanical state evolution and the classical principle of stationary Lagrangian action, as promised at the beginning of this presentation. At this point, we have established our main result, but we haven't yet addressed step 3b. We now evaluate the critical length L sub c for any position velocity time combination. We show that wherein we have previously defined the differential Lagrangian function and now we define the effective mass of the Lagrangian function. Recall that the Jacobian determinant of the velocity to momentum transformation, which is in fact the absolute determinant of the velocity Hessian matrix, also coincides with the effective mass, raised to the nth power. So, we now address step 3b. We look at the integral. In the above integral, the parameters vector x, vector u, and scalar t stay fixed, while only the velocity vector v is variable. Let us examine the first few Taylor series coefficients of the differential Lagrangian with respect to the velocity variable v around the average path velocity u. We recall that evaluating this function at vector v set equal to vector u, we find that taking the first derivative, we obtain this shows that velocity vector v equal to velocity vector u is a stationary point of the differential Lagrangian. Proceeding further, the second derivative of the differential Lagrangian is given by This shows that the second derivative of the differential Lagrangian at the stationary point is equal to the negative of the second derivative of the original Lagrangian function. Let us define a parameter, called mu_min, as follows. Suppose mu_min is strictly positive. This will indeed be the case if the velocity Hessian matrix is strictly positive definite or strictly negative definite. In which case mu_min is the magnitude of the smallest eigenvalue of the Hessian matrix. As long as mu_min is strictly positive, the first derivative, or the velocity gradient, of the differential Lagrangian, is lower bounded by. In particular, this means that v equals u is the only stationary point of the differential Lagrangian. Furthermore, as we move away from the stationary point, the complex exponential term oscillates more and more rapidly. From the well-known principle of stationary phase, we develop an asymptotic approximation of the previously defined integral. If delta tau over h cross is very large, then the complex exponential in the integral typically exhibits high-frequency oscillations that tend to cancel itself out in net effect. The only exception is the contribution of the integral around the stationary point, which remains stable. Based on such considerations, the stationary phase principle says that only a small neighborhood around the stationary point of the complex exponent contributes to the integral. Around the stationary point, the complex exponent is dominated by the quadratic term of the Taylor expansion of the phase function. We know from our previous calculation that at the stationary point, the second-order derivative at the differential Lagrangian is the negative of the second-order derivative of the normal Lagrangian. Therefore, but this is related to a standard integral, which has a closed-form solution. To summarize, we have shown that where is the effective mass associated with the system Lagrangian. In the last step, we have used the standard result. It is easy to see from here that, as required, the above calculations in step 3b are in fact exact, under the special case of a quadratic Lagrangian system, whose third-order velocity derivative is identically zero. Such a Lagrangian function has the form. Clearly, this includes mechanical systems subjected to conservative, as well as electromagnetic force fields, characterized by velocity-dependent potential components. For this Lagrangian, we have the derivatives Of course, the third and higher-order velocity derivatives are zero, because we assumed that the Lagrangian is a quadratic function of the velocity vector. Proceeding further, the differential Lagrangian function is given by Hence, the stationary phase calculations used previously hold exactly, without the need for any approximation. Proceeding further, the conjugate momentum is defined by the Legendre transform, which means this leads to the classical Hamiltonian function. In this case, the Hamiltonian function may be interpreted as the total energy of the system, comprising a sum of its kinetic and potential energies. The effective mass of the given system takes the form. Note that the determinant of a real symmetric matrix must be real-valued, either positive or negative. If the determinant is negative, then its nth root can be a non-trivial complex number. We have thus completed all the steps of our derivation of the path integral equation. In the process, we have provided an exact definition of the quantum mechanical path integral, based on the classical Lagrangian action. We hope this clarifies most of the analytical details associated with the derivation of this equation. Please do send us any questions, comments, or suggestions that you may have. Subscribe to my channel if you like, so that we may share more videos like this in the future. Thank you. By the way, what does my middle initial N stand for?